We are going to be talking a little bit about current and resistance today, and feel free to pause, move forward, skip, all those different things that you know to do to make this work for you in any way that you feel like would be useful or productive for you. So I would suggest having your textbook open and handy because we're going to be referring to that just a couple of times, and then also think about some big concepts and draw back to other things that we have learned so far this year. So my first question for you would be, what do you know about current? So take a moment, pause, write everything that you know about current. If I had to bet dollars to donuts, I'm going to guess lots of you wrote this down. Well, maybe if I can use my pens, hold the phone. There we go. Let's do purple today. I is equal to dq over dt. And you'll find that definition in your on your green equation sheet. So it's the rate of charge flow. So I actually like to think about this more in terms of charge flow rate. So current is charge flow rate. It's how much charge or how many charge carriers are moving past a given point per second. So if you were to look at this strange picture that we have here, our current that's flowing through like this line from A to A prime, right? That current that's flowing through that part is the number of charge carriers that go past that point in 1 second. Same thing here and same thing here. And those current values are all going to be the same, right? They're not going to be different depending on where you're at because we know charge is conserved. That's another really important concept that we have to invoke here in this time. The unit for current, maybe this is another thing that you wrote down. A unit for current we know is an amp. And an amp is 1 coulomb per second. And several of your questions in your homework asked you to find total charge. So if we take a look and we rewrite this function or this equation, and we rewrite it in this format. So dq is equal to I dt. Right, so I essentially just multiplied both sides by that denominator dq, that differential, to get it into what we call a differential form so that it's a little bit easier for us to solve. So right now what you have is a differential equation, right? Oftentimes you're asked on AP tests to write differential equations. This is an example of a differential equation, right? And so if I want to know my total charge and I've got this little dq over on the side, what do I need to do? That's right, we need to integrate. And in integrating that function over time, that's going to give us the total charge that moves past in a given amount of time. And so the nice thing about that is if that charge flow is constant with time, meaning it's in a steady state, then that would mean that the current times the time will just give us the charge that moves past that given point in 1 second. And our big concepts in current are as follows. Charge is conserved. That means that if you have one part of a wire or something called a junction, so, and this is going to lead us right into Kirchhoff's rules next chapter, that this junction right here, there's current that comes in this junction, and the current then goes out this way and out that way. And the amount that goes into that junction has to be equal to the amount that goes out of that junction because charge is a conserved quantity, meaning that the charge is always going to be, we can't make it, we can't destroy it, it's just moved around. So it's kind of like water flowing through a pipe. If water comes in, the pipe, water has to go out of the pipe, or pipes in this case. That's also true if you have kind of a crazy little like shape that looks more like this, right? This shape is a lot different, but it's still the same idea that current that comes in is going to be equal to the sum of those two currents leaving that junction. And then the second idea is this thing called conventional charge flow. And this is the thing that's a little bit hard. So when we talk about a convention is not a whole bunch of people getting together at a hotel about, I don't know, whatever you want to have a convention about, maybe electronics, maybe games, maybe teaching and learning, those conventional charge flows. Convention in this case means like accepted, or how we talk about it as physicists. So a conventional charge flow is going to be our the direction that we assign to charge flow, and it is in the direction of positive charge carriers. Now, we know that that's not really what happens inside of a wire. We know that it is actually those valence electrons that are moving and in the opposite direction of a positive charge. You can think of it, and maybe I'll blow some synapses here, but you can also think about it as the movement of holes. So as the electrons move, let's say I've got electrons, here's my wire, right? And a conventional charge says that let's say my current is going this way, right? I'll call that my I, that's my conventional current, right? And so that should be positive charge carriers moving in that direction to the right. But we know that it's actually the little electrons, right? We'll draw those in green. Our little electrons here, our valence electrons, are actually moving that direction. But the green, those electron movement, is not what we're studying. What we're actually studying is a conventional current, which is this I, right? And if we think about that, we can think about it as the movement of holes. So like this little guy here left this spot to go there, right? And so that movement of those holes actually moves in the direction of the conventional charge flow. That blows your synapses. Don't sweat it. Just think about the current moving in the direction of positive charge carriers, and just kind of turn off the idea that we know that electrons are actually the things that are doing the moving, which I know is a little bit tough, but you can do it. All right, so let's talk a little bit about current densities. Current densities are useful. This isn't an idea on the equation sheet. So for instance, this crazy equation that you see isn't there, but it is a super useful idea because current density is used to help us define an electric field within a wire. Also, current density is important because it allows us to think about how much charge is flowing through different parts of wires depending on their structure. One of your homework problems uses this idea, and I want to connect it to one of our past AP problems on our last test. That was a little bit tough for us, and hopefully those two ideas will connect together. So just bear with me a little bit. I know it seems like a little bit of a stretch, but okay, so our current density, and it's just like any density, it's something per volume or per area. In this case, it would be per area. So it describes the flow of charge through a cross-sectional area. It is actually a vector quantity, and that vector is in the same direction as the velocity of the moving charges. So over here, we're like, yeah, we're just gonna talk about positive charge carriers, and we're gonna do conventional. And then over here, we're like, oh, just kidding. We are going to talk about the direction of moving charges and the velocity of moving charges. But we can still do that in terms of positive charge carriers, right? And I would have you do that and think about it that way. Okay, so to clarify the direction of the current density, I want to make sure that I'm super clear on that. It is in the same direction as the moving velocity for the positive charge carriers. So those are actually consistent with each other. So I want to make sure that I was super clear there. So if we've got our charges, let's say, moving in this direction, there's our conventional current, and we have a cross-sectional area, right? So just pretend that that's a circle. Here's my cross-sectional area. There's dA. Actually, that would, I guess, just be A, wouldn't it? That whole big thing would just be A. The little bit would be dA, right? The little, if we wanted to like, that would be a dA, right? And in that case, that current and that density would be in the same direction. So again, current is going to be the dot product of that density, J, and the area vector. So essentially you're like adding up the density per the area. So if we have a constant density or a uniform density throughout that whole purple space, as you can see, that's uniform, like those lines demonstrating like the current moving, those are uniformly spaced, we can find that using this equation right here, right? That our current density is just our current time divided by our area, or you could take your current density times your area to get your current. You could do that same idea down here, right? So if we look at our green cross-sectional area versus our purple cross-sectional area, we know from our previous discussion that the amount of current that's flowing through the purple cross-section is the same as the current that is flowing through the green cross-section. And we kind of just, I think, intuitively understand that the current density is going to be greater through that green section since there's a considerably smaller area. That doesn't necessarily mean that the charges are moving faster, which is something that's a little bit tough for us to understand. There's more of them moving because remember, a current is not a speed, it is an amount of charge that is moving per second. So I want to take just a moment and look at our number, and instead of number 15, I want us to look at number 13, which was one of your homework problems. And I'm not going to do this whole problem out for you, but there's one key concept that I want you to look at. So if you haven't looked at 13, look at 13. And I want you to start kind of thinking through that. We're going to work through just part of part A, and I'm going to just point you in the right direction so you can go and finish it on your own. If you've already looked at number 13, I want you to look at it again with me, just so that we have a very clear understanding of what is happening and why things are the way they are. So I'm going to ask you to pause for a moment, get out number 13, and then look at it, read it, and then we'll dive back in. Okay, so now that you had a little bit of time to reorient yourself to that problem or look at it again, a couple things that we need to pay attention to. So in part A, we have a current that changes with the radius. And so a current density that changes with radius. And so their current density in is a function in that cross-sectional area is some constant value, that J naught, times R divided by our capital R. So let's just define a couple of things. So from here, from that center all the way out, so what you see those two circles is obviously the cross-sectional area. And then, so this radius is our capital R there. And then our smaller radius is going to be, our little r is from here to that smaller circle that I have drawn in there. And I've drawn that in to represent this little guy right here, right? This ring right here. That is our differential dr. And you're going to see why we're going to need to use that in just a moment. But know that the current at radius little r, that little r right here, is a current density is a function Ja is equal to that constant J naught times radius divided by the radius of that whole wire. So there's a couple things that we need to look at. First of all, we need to look at our dot product. And we need to deal with our dot product. And so what we will do is we will assume that our angle between our cross-sectional area and our current density is 0. So therefore, this statement will simplify to I is equal to the integral of J times dA, right? Our current density times our area. Again, and so J and dA is going to be equal to the angle between those, sorry, is going to be 0 degrees. Okay, so once we have that simplified a little bit, now it's time to start thinking a little bit more about how these two things really kind of work together, meaning the current density and the area. So we have our dr, this little guy right here, right? That little between here and here. And then that dA would be that whole like big area there. Are you following me? Like that is our dA and our dr is that little teeny bit in there. Maybe I should make that a little different color. Here's my dr, right? And that whole color in there is my dA. And so what we want to do is look at our function and plug it in our statement here. So we're going to take our function, we're going to plug it in our statement, and then we're going to figure out what it is exactly that we need to do with that. So I'm going to hop down here a little bit and write I is equal to integral of, and then we'll go ahead and put in our equation, right, that we had before. So our J naught times our R divided by our capital R dA. Okay, so I'm hoping that you're starting to see an issue with our integration that we're going to do. So right away, you should notice what's constant and what's not in this. And what's going to be constant here is that value and that value. And so what we're going to be integrating with respect to is this R value right there. And oh, I do not want that anymore. How do I get a regular pen? Oh, you guys are so sweet for bearing with me and your technologically challenged teacher. There we go. I just changed it there. There we go. I got it. All right. And so we're going to want to be looking specifically at this value right here, right? That's going to be our variable, right? Our R as radius increases right here. But you're going to notice that when we take those two constants and move those out front, our radius here, our density, our current density has been written in terms of R and not in terms of area. So we have a problem that we need to solve. And we need to use some geometry to do that. So what we're going to do now is we're going to rewrite our dA. So we're going to be focusing on rewriting this dA because this variable R needs to match with that variable in order for us to actually do that integration. And so if we go back and look at our picture a little bit, if we think about this little guy is our dr, right? And then that whole cross-sectional area that is shown in purple, that's going to be our dA. So if we think about how we could rewrite dA, does it make sense that I could rewrite my differential dA as being 2 pi r dr? Meaning like that purple circumference there, right, which is the 2 pi r, right? If I integrate that over that dr there, I'm going to get that area of the purple. Does that make some sense? I hope it's making some sense. You can't answer me, and this is what makes this hard, but hopefully you can make that make sense. You could also think about this in 3 dimensions, which is what we needed to do on our last test. We could think about those shells and then adding up, I think it was charge that varied with the radius. If we add up the individual shells, so instead of like a circumference adding to like kind of like a thicker cylinder, hollow cylinder, we would think of like a shell adding up to a volume. Okay, so that's just a little thing that we could throw in there for you to think about. Okay. So then we're going to take that substitution and put it in for our dA. And then after that, the rest is, you should be fairly home free. So let's go ahead and just pull our constants out because, hey, why not, right? And then we're going to have R, and we'll have 2 pi r dr, right? So I just took this right here and substituted it in. We would obviously then need to do some simplification, and we also need to put in our limits of integration. So I'm hoping that you're like, oh, our limits of integration are pretty straightforward and pretty simple, right? So I'm going to rewrite and simplify. Let's see, we're going to have 2 pi r also come out front. No, just 2 pi. R is our radius, and then we still have our current density value, our constant there, and then our big radius, the radius of the whole wire, and then we have our integration here. That's going to be from the center all the way out to capital R, all the way out to that very outside, right? And then that would be, so we got R, and then R squared, dr. So hopefully you can see, I'm not going to do the rest of that integration for you. That one's a pretty straightforward, easy one. The next one's a little bit tougher, but I think that you all can handle it. You can do it. The two big ideas that you needed to get out of this are the following. That this dot product you have to deal with. So our cross-sectional area that we've chosen is has an area that is in the same direction as the current density. Remember, area vectors always point perpendicular to the surface. So if we think about the wire that you see in front of you, if the current is coming directly out towards us, that area vector is also pointed directly out towards us, right? Because it's perpendicular to that area. So that allows us to simplify this dot product, get rid of the vectors, and then we are left with this function here. When we substitute in our function for our current density, we notice that it is in terms of R instead of in terms of area. So then we need to rewrite that differential dA in terms of a variable that matches R. And when we do that, if we look back and we look at our circumference here, so that purple is our dA, and this little guy here is our thickness of that circumference. That's our dr. We add up that, we will end up with our area, right? And so our little differential area is just our circumference of where that location is times that differential dr, how big that little infinitesimally small radius is. And then we go and integrate our function, simplify our function, and then get that in terms of our limits within 0 to R. So hopefully that gives you a little bit of a nudge. Maybe you didn't need the nudge. Maybe you skipped over this part. All of that is fine. Use what you need. Skip over what you can't, which is nice, right? You don't have to listen to me if you don't need to or want to. Let's talk very briefly about drift velocities. So drift velocities are actually really small. What you want to know is that there's a really great derivation in your textbook. This equation that's in red, that is there for you on your equation sheet. So let's just make sure we know what each of these terms are. Then we'll talk a little bit about drift velocity and then power, and then we'll be done. So, okay, so our current here, so this whole chapter is all about current, looking at it in different forms. So our charge carriers within a wire move very slowly, and they also move very erratically. So just because we have an electric field in a wire that is causing charges to move, or we set up a potential difference across a wire that causes charges to move, that doesn't mean that they move all in a straight line like they're in a marching band, right? That's not really what happens. They're moving all over the place, which you can see in this, like, right, this little thing. But the electric field that's applied, all right, so the electric field image is applied to the right, is going to cause those charges to drift. And so they're going to essentially have like a net movement. Even though the charges are moving all randomly, they're going to have this net movement. Notice that the movement of those actual electrons are moving opposite of the direction of the electric field, which is okay, right? We know that that's going to be true because those negative charges move in the opposite direction of our electric field. So in this case, like our conventional charge flow would be moving to the left, and our actual electron movement, our drift velocity of our electrons, would be moving to the right. It is typically very slow. These things are not moving quickly. So a question that I like to ask at this point right now would be, if you flip on a light switch, why does your light come on so quickly? Like, it's instantaneous. You can't even tell the difference. It is not because the charges move really fast. They don't. They move actually very slow. The field in the wires that causes all of the charges to move happens instantaneously when you flip on that light switch. That's what makes those charges move. The charges are already in the wires. The charges don't come from the switch. They don't come from a battery. They're already present in the wires. Simply closing the switch or connecting a battery allows those charges to be pushed via the electric field, right? Okay, so that drift velocity again, can be found using this idea, or I should say our current can be found using our drift velocity. So if we take, and this equation makes a whole heap of sense if you just think about it, how fast the charges are moving, right? How fast the charges are moving, the size of the charge, right? So this is our fundamental charge. What's 1.602 times 10 to the negative 19th? Right? That's the fundamental charge. Oh, that's a really big negative sign. Sorry about that. That's not a subtraction. That's just a 2 to the negative 19th power. I tried to use my mouse. Epic fail. Ooh, now it's a different color. Nice. Okay. And then this N right here is the number of charge carriers per volume. It is just a simple like a property of materials. So metals are going to have a lot more charge carriers per volume than, let's say, non-metals or insulators, right? And then we multiply that by our cross-sectional area to get our current. A couple of fine print things that we need to make sure that we understand. This really is only going to be valid if we have a steady state. And you've heard me say this before already, haven't you? You've heard me talk about a steady state in terms of moving at a constant rate, meaning we don't have current that's increasing or decreasing. That current stays at a constant uniform rate over time. This is set for positive charge carriers, and then the electric field is set up within the wire that is caused by a constant potential difference, and that the charge density is uniform through that cross section. So there's a lot of like, it's got to be just so in order to make that happen. In order to make that equation work. So a couple of things just to watch for is we got to have a constant steady state current. We have to have a constant potential difference that's causing that. And then we also have to have a uniform charge current density throughout that area. All right, so to finish up chapter 6, I feel like I'm sprinting here through a marathon, but to finish up chapter 26, it does talk a little bit about power. Power is not a tough concept, but we do need to make sure when we use it next chapter that we have a basic understanding. So power in a mechanical sense is the rate work is done. We've already looked at mechanical power, but we can also look at it in terms of electrical power. And so a watt is something that you will see frequently on like light bulbs, right? 100-watt light bulb. Old incandescent bulbs would be rated in watts, which is how much energy is converted per second. And so a power in an electrical sense is just our current times our potential difference. And you can see that this, and to be honest with you, this should have a red box around it because this is also on your equation sheet. This is our definition for power. And if you have ohmic devices, you can use Ohm's law to get other equations for power. So there are times when you will need to substitute some of those different values into your power equation. But remember, this only applies when you have constant resistance. So that resistance has to be constant. Okay. That's all I have for you today. Be well, wash your hands, stay away from other people. I care about all of you and each and every one of you, and I hope that you're doing well. Use your resources. AP is supposed to be putting out a bunch of stuff. I haven't had a chance to look at it yet, as that just came out today, but don't be shy. Reach out if you need something or if you want to ask me any questions. I'm not sure exactly what my limits are in terms of my ability to respond to you. I obviously want to talk to you as a person, but I'm not sure what they'll allow me to do. The Department of Ed has put some fairly strict guidelines on what I have the ability to do and not do. I want to make sure that I provide instruction in an equitable way, or actually not provide instruction, excuse me, but provide resources in an equitable way with opportunities. So take care of yourself, take care of your family, and I will be posting more stuff on Google Classroom soon. All right, take care.